So Chad had the northernmost chord, and then there was another observer in southern New Jersey who got one just 10 kilometers north of him. And that was very close to the prediction. Yeah, you're in one of these three here. Yeah, you're here. Green line. Yeah. Yeah, Smith. Yeah, here you are. Yeah, the green line. Yeah, this one here, I guess. Yeah. Yours will be between 8 and 9 days. Uh-huh. Yeah, maybe. Okay. So, if it's time, do that. Yeah,
and then you've got one more presentation, right?
Okay, yeah, I have about 3 presentations or 4, yeah. Yeah. You have to fill your attachments.
Okay. I'm turning on audio. I will have to let you all tell me if you can hear me and if everything is correct. Okay, I'm also waiting for Steve's getting my presentation up and running. I don't see it just yet. Yeah, you hear me. I killed there's no need for my video camera. I figured it would cut down on bandwidth. If y'all really want to see my mugshot, I'll be glad to turn my camera on, but just figured I would spare bandwidth. Brad says he doesn't want to see my mugshot, so I don't blame him. Okay, the reason we're having to go to this particular method of show desktop through Steve's computers, I have several animated GIFs that do not seem to work in presentation mode. And we only discovered this right at the end, but we found this as a fix. I'm assuming I'm up now, right? Am I supposed 1 minute? Okay, thank you, Ted. Okay. Now I am seeing Steve Mesner's version, but I thought y'all switched over to Terry. How do I know what slide we're on, or do I just go ahead and go? I need someone to tell me. Go ahead. We'll match Steve's. Okay. Okay, alrighty. I'm going to go ahead and go. If I overtalk a slide, I've asked someone to tell me that I'm talking too fast for what slides are appearing there, because there is a delay on our end here, it seems. My presentation is, no, go back, Steve, to the first slide. My presentation was intended to be a call for observations, but I was asked to present some interpretation of past results and expected future results. So unfortunately, this is going to be a very data-dense presentation. I will encourage all of you to download it from the presenter's website and look at it later. I'm going to probably move at a pretty brisk pace because I'm essentially making two presentations in one. The key to this opening slide is to demonstrate a particular phenomenon of scattering. At our sunset, we see our sun turns red, orangish red, and that's because the very short wavelengths of blue and violet are scattered away by particles in the atmosphere. So there's more than just a pretty picture in this opening slide. Let's go to the next slide. This is a schematic diagram to demonstrate, for me to try and best convey to everyone what we think a Jovian extinction event is in geographical orientation. See the Earth view at the top, and you see Europa's motion moving along from our viewpoint on Earth. The tenuous particles surrounding, I'm going to call it Io. The correct pronunciation is Io, but I'm just going to call it Io since everybody's used to hearing that. So, so as Io's tenuous material that surrounds Io passes between the Earth view and Europa's view, we see this scattering of photons that's creating a dimming in the shoulders and the wing data outside of the occultation. Next slide. And so there's a concept that this is a little beyond what we normally do at Iota, but is a concept for you to understand fully what we have found as the source of Jovian extinction events. The visible spectrum of light, you can see, is broken down into these wavelengths of light. I've also included common filters that photometrists will use. Now, the purpose of a filter is to eliminate all other wavelengths other than a sample band of wavelengths. If you look at the red, for instance, a red filter will typically get the red spectrum from 620 nanometers to 750 nanometers. Keep that in mind as we move along. The filters eliminate and do not sample other wavelengths. That's key to what we have found. Next slide, please. Galileo space probe sampled particles around Io and found them on average to be about 600 nanometers, which is the same as 0.6 microns, as you see displayed. And we've done differential color photometry now. This is actually a CCD image, so it was incorrectly stated that we are not using CCD technology. We have been since 2012. This multicolor CCD image demonstrates particle size differentiation, in that blue photons were scattered much more than red. Red was not scattered much at all. Next slide. Which, as you saw, matches the Galileo, what you would expect for a 600 nanometer particle, and this is also outside. You'll need to read up on this if you want to understand more. It's a generic description to display what the Rayleigh and Mie scattering photons is. And that essentially Rayleigh scattering occurs when the wavelength of light is larger than the particle size it encounters. In Mie scattering, the photon wavelength is approximately the same size or smaller than the particles the photon encounters. So this is sort of a schematic view to get you to understand that basically red, orange, and yellow, and green to some extent aren't affected as much by 600 nanometer particles as violet and blue photons would be. They fall into two different regions, Rayleigh and scattering. And that explains the CCD differential color that we see at the bottom left. Next slide. So I'm going to go over a lot of generic things that people toss out, and the thing is you got to do your homework with Jovian extinction work. You can't use generalities. You have to dig into the details, because the devil is in the details. I get this as one of the most common questions: why can't I see the atmosphere surrounding Io when it transits Jupiter? The answer is you can, but you got to do your homework. Next slide. The devil is in the details. Here is just 6 of the first order details. Again, you want to download it. I'll hit these pretty quick. Hubble uses filters. You have to understand what filter is used in the Hubble image to understand what photons are being sampled and what photons are being excluded. If you get an image where 500 nanometer or shorter wavelength photons are being sampled, you have a chance of seeing some extinction. These filters are narrow band, so they're not even sampling a wide range of photons. So you are excluding the broadband visible spectrum when you look at a Hubble image. Jupiter is also an illuminated sphere, meaning it has a constant gradient from the center working out. Plus, it's very mottled in appearance. It makes a horrible backdrop. So, using Hubble to see the atmosphere of Io is not fun, not easy, but it can be done. For Europa, the radius of Europa's atmosphere is 44% of Jupiter's atmosphere. So you cannot derive a background trend easily to be able to normalize any sort of sampling of data surrounding Io, or excuse me, in this case, Europa. So we don't even recommend, I see no way of really doing a good Europa atmospheric measurement as a transit. Got to do pixel binning because of all the noise background of Jupiter and its modeling. And so number 6, the detail is the Io transits are ideal if the appropriate wavelength is sampled. Next slide. So not picking on Tony Malama, I actually applaud you, Tony, for taking the time. You were the only person that has published a paper about Jovian extinction other than our campaign. So let me just say that so that you don't think this is a personal attack on you. What I'm doing is highlighting some examples in Malama's 2013 paper in which he shows a Europa transit, but it was incorrectly labeled as being 410 nanometer filter used, when in fact it was 544 nanometers, where little if any extinction would have been detected if there was any. It also is a Europa transit, and so therefore there's virtually no way to get the background trend, because Europa's atmosphere is 25 radii, or out to about 20 in the extinction that we've seen. And then Malama claims that we would have claimed the red line is what should be seen, and we would never have made this claim because based on the details that this was a 544 nanometer filter. Anyway, we'll move on to the next slide, because I'm going to show you some examples of how you can do it. So if we look at where that particular image falls in the spectrum, at 544 nanometers, you're above into some Rayleigh scattering, but no me scattering of the shorter wavelengths. What you see at the bottom left is the actual Hubble header information for this image, showing what I was saying, that it is not a 410 nanometer filter. It was a 544 nanometer center wavelength filter used, and it only sampled 1/10 of a micron, or 100 nanometers bandwidth. So again, as I pointed out, filtering is narrow in sampling. Next slide. Now, where Malama almost got there, and let me help you with this so you can see that in the Io transit, that he had in his paper in 2013, Figure 1, shows an ion transit, but incorrectly identifies it as being used a 555 nanometer filter, when in fact it was a 409 nanometer, making this a perfect candidate down in the violet, sampling violet. In his scanned luminosities, he again didn't do any background normalization to be able to see what the true trend was. And again, these are all the tiny details, and also the red line represents what he thinks we would have claimed as a 15% extinction, when this is a very narrow band. In fact, if you go to the next slide, is a very narrow bandwidth. If you look down in the header information, the bandwidth of this filter that Hubble used was only 15 nanometers wide. A very narrow band of photons were sampled. So even what extinction we would find would not be the total broad band of 15%. But we do see the placement of where it is in the spectrum, and it is ideal right there in the violet. So let's go to the next slide, and I can demonstrate how to correctly do a transit of IO across. Next slide, please. I still don't see next slide. Oh, we froze up. There we go. So this is how you can correctly do a IO transit across Jupiter. First, you have to identify that the right wavelength is being sampled. Next is that I had to sample the intensity gradient outside of Io's atmosphere to establish, at least at a minimum, a first-order trend. It's impossible to establish a perfect trend. It's just impossible because Jupiter is not evenly illuminated, nor is it evenly, its surface is not the same. But so I bend vertically 4 Io radii worth of information in a 16 Io radii box. You see that the top box represents the background trend. The box surrounding Io represents the atmospheric trend. And then you see the light curve where I normalized the atmospheric trend with the background trend. And you can see the extinction that occurred surrounding Io out to about at least 8 Io radii. And it's about 40 millimag. So again, as I pointed out, you would not expect to see the full broadband extinction of about 0.15 magnitude because you're not sampling all of the broadband photons. Let's go to the next slide. By the way, I want to encourage everybody to data mine Hubble images and do exactly what I did. There's nothing special about what I did. It's just paying attention to details. The next challenge, the IMCCC challenge. Why in the FEMU, which stands for the Mutual Events Phenomena season, why is it we don't see it in the IMCCE light curves? Well, the answer is you do, but you have to understand a few things. Filters are used, and as you saw, even Dave Harold presented when he presented on mutual events. Let's go to the next slide. Presented on mutual events that he recommended you use a red filter. If you go to the FEMU, the IMCCE technical notes, you will see that they say use a V, R, or I filter, and with an emphasis on R. I is a little trickier to work in, and V is okay, but they mention, as Dave Harold mentioned, to use an R. Well, as you can see in our little spectrum, little schematic here, you're sampling photons that aren't in the scattered region, in the Rayleigh or scattering region. And if you remember the differential color photometry I showed you earlier, red is barely scattered while blue was significantly scattered. So one of the reasons people in the entire IMCCE database aren't seeing, or I should say have flat wings outside, is because they're not sampling blue and violet, or green, or yellow, or orange. They're sampling red for the most part. Let's go to the next slide. If you do your homework and you go through the IMCCE database, you will find, I just pulled two out that I saw recognized had extinction event trends in the wings, and they match pretty much a lot of the trends, about 8 or 7 or so in these cases. If you go through the database, you will find people that likely did not use filters, used a clear filter, what's called a clear, unfiltered, and they have extinction trends in them. Now, here's a question I get asked. Do you know that these were unfiltered? The answer is no. If you go through the IMCCC database, there is no record in the archived data of what filter was used. There's no way to correlate whether or not this is filtered or unfiltered. My entire point on that is that IMCCE data cannot be argued either for or against Jovian extinction events because of insufficient ability to produce the information needed to derive where the data came from. Let's go to the next slide. So, in doing a real quick summary, what we see is FEMU data is not likely to show Jovian extinction events because it's sampling outside of the scattering region. The Europa transit that was in Malama et al. Was outside of the scattered region. However, the IO transit was, and what we have sort of come to is that we need to be sampling less than 500 nanometer in the blue and violet and UV in order to find the extinction events, because this is where the scattering is taking place. Let's go to the next slide. Here's another example of one reason why IMCCE data really isn't usable as far as doing the search in most cases. 6 to 10 minutes of wing data outside of an occultation is taken. You see a light curve. This is the exact same event with 6 minutes of wing and with 2 hours of wing, an hour on each side of the event. And you're just not seeing, you're not sampling in time. This time it's not a spectrum issue, it's a time issue. You're not sampling out to where the extinction events are occurring. Next slide. Another popular statement I get, the 1971 occultation of Beta Scorpii C by Io showed no extinction trend, therefore JEE can't be real. Let's go to the next slide. So here is the details, the devil in the details. This is an invalid argument. It cannot be used for or against JEE. If you look at the actual plot, the time scale is 30 seconds. 30 seconds. If you do your homework, you will find the extinction event would have started 1260 seconds prior to the ingress of the occultation. 30 seconds is not enough time. In 30 seconds, Beta Scorpii only moved 0.2 Io radii. You would have to go out 21 minutes prior to have seen the extinction event. So this really isn't an argument for or against. This kind of just doesn't fit in the argument. So let's go to the next slide. So I'm calling these uninformed statements. It's just a lack of homework and being able to, people make general statements, but they haven't done the homework to really verify those statements. Video cannot provide accurate photometry. Let's go to the next slide and we'll discuss that. I issued a video challenge to several professionals. No one will take me up on it. So far, no one will take me up on the CCD photometry challenge. I have said I will do a target, you will pick the target. I will do it with my video camera, you do it with your calibrated CCD, and let's see what I get versus what you get. Nobody took the challenge, so then I said, well, what can I do? What's the hardest thing I can think of to do with a video camera? And I thought exoplanet transit. So, go to the next slide. So I did one. I did one with, this is HD 189733B. My video data is on the left. On the right is CCD data, calibrated CCD data. And what I need to draw your attention to is at the very bottom is the residuals. And the residuals represent the deviation from the fit. And my residuals were approximately one standard deviation was 1 millimag. As you compare that to the one on the right, which is maybe 10-ish millimag. So not only can be, and this is 3.5 hours of data, mind you. This is a 3.5 hour event. So I keep hearing people say, well, you know, video is okay for short periods, can't do long period photometry. I did nothing special here. I imaged a star. I used a reference star in the field of view. I used Live Movie. I used Excel to bend 900 video data points into a single point, and then I did a moving average of about 30 data points, and my data is much cleaner than a standard CCD camera. So let's go to the next slide. That just sort of answers itself there. Video is quite capable of doing photometry. Here is a JEE event that apparently, not picking on John Menke, but I guess he didn't want you to know or see. He ignored calibrated CCD images. I asked him why he ignored the 3,000 I sent him. Here is the CCD data at the bottom in multicolor compared to the exact same event at the top in video. Exactly the same trends. And so you see in this particular case, the material from Io's atmosphere is trapped in a torus ring. Io passes through collimated lines of this and suffers self-extinction out of the tips. That's a whole other discussion we won't get into. But this is sampling Io's atmospheric material, and we see that we get the differential photometry shows particle size discrimination, and we see video matches calibrated CCD data. So we'll move to the next slide. I'm not going to go through all of this. I'm going to hit the highlights, but you can go back and read. Here's the different noises. You have systematic noise, you have random noise. We have taken all of those into account. We do heavy binning. We bend, so atmospheric scintillation, if you bend 10 seconds of data or integrate for 10 seconds, you will statistically remove atmospheric scintillation. So using that premise, and that's in Brian Warner's book on photometry, if you want to refer to that in my references. We bend a minimum of 300 for NTSC, 250 frames for PAL. That represents approximately 10 seconds of data. So we statistically eliminate our Earth's atmosphere scintillation. And we also beat back all these other noises to where video photometry actually wins by the sheer volume of data we can leverage the statistics. Let's go to the next slide. Oh, good. The animated GIFs are working. Uninformed statement number 2. Video cannot be calibrated. Well, this is absolutely untrue. If you were to take the time and put a lens cap over your observing system and record some calibration frames to average together, there are 5 simple lines of code in an AVI Sense script. I've been posted. There's the link onto my website. You can download, you can just cut and paste those lines into your AVI script and create your own background frame. And upper left is a 2-second integration. That's Saturn, that's very bright and glary. Most of the stars you see are actually moons of Saturn surrounding Saturn there. But on the right is the calibrated version where you see all the hot pixels removed. And if we go to the next slide, even better, you see that the image is flattened as well. What I find the majority of unflatness for our video cameras is thermal noise. So by taking that calibration frame, you get a chance to subtract the thermal noise too. So what you see is the raw pixel intensity versus the calibrated, and you see that it really goes flat. The response is flat. Again, the hump in the middle is Saturn's glare, which I left in the data so that you could see it came from those images. We'll go to the next slide. Also, uninformed statement number 3, the glare from Jupiter makes it impossible to get accurate photometry. Those of you who have done lunar occultation reductions know this is not true. We do lunar occultation reductions right up against the bright limb of Jupiter, of our moon, by configuring the background apertures tangent to the bright limb. The same applies from Jupiter. You see the yellow measurement aperture is reading 0 at the bottom, and I have it right up against the limb of Jupiter. So yes, you have to pay. These are the details you have to pay attention to in a reduction, but they can be subtracted out of a reduction. Let's go to the next slide. All right, uninformed statement number 4. Gamma is causing our the dimming in our extinction events. That's simply not true. We have a mixture of cameras of 0.45 and gamma of 1, and as you can see in this, outside of the occultation, the dimming occurred by Dave Clark at a gamma of 1 equaled the dimming that occurred by me at gamma of 0.45. Gamma has long since not been an issue, so we don't worry about it too much, because as long as your reduction is done correctly, it is not effective reduction. Next slide. Uninformed statement number 5. Camera responses from merging intensities cause our JEE trends. So let's go to the next slide. And we're going to go through a series of slides here to show how we have done our due diligence. You saw this earlier today, John Menke talking about the saturation effect. And indeed, saturation is bad. We actually eliminated from all of our data whenever it is discovered. John did. I thank you, John, for actually finding this 15-minute section of saturation. But if you notice in the light curve, you can actually see where it goes flat and quits responding when the saturation appears. So it is actually see where the saturation occurred, but everything outside of saturation is perfectly valid data. So let's go to the next slide and show you where we tossed out the saturated portion of the video, but the JEE trend is still present in the rest of it. Let's go to the next slide. And saturated data is rare, but ask anybody in that room that's done Jovian extinction event. All of us have had an observation tossed out due to saturation. We don't use saturated data, so that is one of the things that we pay attention for. It just was not caught in that particular 15-minute video. Let's go to the next slide. Now, this is a sample of video I sent to John, Menke, but he didn't seem to refer to it. Up at the top, you will see an intensity map. And at the top is a top line showing where the 100% saturation is. And you see that this entire event is outside of saturation. So any Jovian extinction events observed can't be linked to saturation because we weren't in saturation. Notice on the far left at 312 UT, if you can read that, the peaks, Io, in this whole sequence, Io is on the left, Europa is on the right. And as you go through from left to right in time, you see that the peak of Io starts to shrink. The peak of Europa on the right starts to shrink relative to Io on the left in time. So let's go to the next slide. We break this down a little bit further. Two different observers, same event. The blue bars you see over the peaks at the bottom is not the saturation level. They are placed for imaging, for your ease of observation. Is that you notice at 314 the relative height of Io on the left and Europa on the right, and then at 326 Io on the left and Europa on the right. For both T. Redding and S. Degenhardt, and you can see that the peak on the right dimmed. You can also see the photometry at the top. The light curves show that we took Europa dimmed relative to Io's light curve on the upper left light curve for T. Redding. His image was taken at such a high magnification, we were able to separate the two peaks and measure their intensities before they merged. And you see that the JE trend clearly shows Europa dimming. And then on the right, upper right, you see we overlay Terry's on top of mine, done imaged completely different, reduced completely different, yet lays right on top of my data. You don't get this if this is random noise. Let's go to the next slide. Or random camera response. And I might mention there is no mechanism by which a camera can randomly pick the moon in the back to shrink its intensity relative to the other. I'm 10 minutes over. I started 10 minutes late. Let's go to the next one. Okay, so I'll just let you all go to this on the presentation, but here we have randomized everything. Here we did combined photometry on the left, where both Io and Europa were inside an aperture, separate photometry on the right, and combined the two, and they gave exactly the same result. And also in this case, we used an 80 millimeter finder scope for the image on the left, and a 14-inch Meade at high magnification on the right, decoupling any PSF that could be causing this. So let's go to the next slide. I'll try and go through these faster. Go to the next slide. All right. This sort of explains it all right here. This is there is no merging intensities. We have a lot of these events. This is a near occultation, or what I call a conjunction. No merging moons. Two independent observers, Ernie Iverson and I, got the same trend. And when we invert the light curve and overlay it on JPL ephemeris, we see it fits within that 20 Europa radii approximate Jovian extinction event model. So there is no merging here yet. We get extinction events. So let's move on to the next slide. Okay. This demonstrates the path of the moon behind, passing behind Europa. The dots represent the paths of those, and 4 of those 6 paths do not involve occultations. We've been very busy while Jupiter was not edge on. We've got plenty of conjunctions that occur outside of occultations. So the extinction work is not limited to occultations. Let's go to the next slide. When we overlay our extinction data, you see that they all fit neatly within those 20 Europa radii. You would not get consistent results if this is random noise. Next slide. Don't know if you got that, Steve. Next slide. I'm frozen. I'm frozen on the Europa extinction. Anybody still hear me? What are y'all saying? We freeze. Can someone type me something? Can you hear me? Are we live? What's going on? Am I gone? Am I here? I don't know what happened there. Okay, so I think I am seeing the next slide now. All right, wrapping this part of it up, we're not reporting anything new. JE data models match published model. Let's go to the next slide. Here you see that published data show that the atmosphere of Europa could extend out to 25 times Europa's radius. We're not making this up. There are gravitational models. You got to do your homework on this. Next slide. And you see that we're showing approximately 20 radii of extinction data. So the extinction part of it seems to show well. I don't know if you got next slide. There. So for Io, by the way, this was done using mutual events from Snyder et al. You see that it says that its density falls steeply out to 6 radii and more slowly outside. So it's expected to extend out to 10 or 12 Io radii, which is what we are measuring. We measure anywhere between 7-ish to 12-ish Io radii. So we're matching published results. We're not making this stuff up. Next slide. And as far as we're not claiming a dense atmosphere around Io, we're claiming we actually match what the measurements are. The measurements taken by Snyder et al. Of mutual events gathered a particular density, and the red square matches what our calculated density that we derived from our observation. So we're not claiming anything to be denser than is in published data. It's just what we see. Next slide, please. Okay, so now we get to where I'm supposed to be, although I know you'll probably want me to wrap it up. Here is the, you're going to go to my presentation or my website, and you can see how to best observe Jovian extinction events. All we're saying is when you're watching a mutual event this season, please observe a little bit longer before and after the event. Observe with a blue filter or unfiltered. If you can't do a filter, just go unfiltered. There's other instructions here. Please just, if you're interested in observing, download that presentation or go to our predictions and get that. Next slide. I'll give you a sample of what the predictions look like. These lines represent how close the separation was, line of sight of the body in back versus the body in front. The dashed line at the bottom represents an occultation. In other words, the body of one actually passes behind the body of another. And as you can see, you can actually see where the occultations begin. But more importantly, outside of the occultations, there are a ton of conjunctions. So of the hundreds of mutual events, there are hundreds more Jovian extinction events if you want to participate. Let's go to the next slide. This is Io. Io in front. The gap in the middle represents where right now Jupiter's in the glare of the sun. Once in September, it emerges from the sun. Long before the occultations begin in November, there are a number of conjunctions where we can get chords through the atmosphere of Io. You're welcome to join us for that if you want. Next slide. Next slide is the same thing for Europa. There are a bunch of conjunctions that aren't occultations that will allow us to measure the atmosphere of Europa. And that's what these lines represent. Next slide. Shows what the predictions will look like. Well, no, this is a zoomed in, a quick view that's zoomed in showing an individual day, and each line is 0 hours UT on the vertical scale. So therefore, you can look at the relative position to estimate if it's in your UT time of visibility. Next slide, and then the next slide. Okay, here's an example and I see this animated GIF is not working. But what you will get in the predictions, for Io and Europa, we have a basic working model of their atmosphere and their expected extinction. We will give you the estimation of when that extinction begins and ends for conjunction. And in the event of an occultation, we see that we've removed the occultation That's the gap there in this particular light curve, but the extinction is the line you see outside. Give you an idea of how long and when to observe. Next slide. And there is a detailed file for minute by minute in there that you can also, actually I believe it's another 2 minutes, that will give you the separations and visibilities and all that information. Next slide. So you'll find this in each one. There is our link. We have a discussion group. I'm available to discuss this at any time. You download this presentation and there are all kind of references at the end. So I guess we'll call that a wrap. I hope you can join us. There's lots of events to observe outside of just mutual events if you're going to do mutual events. Thank you.
Possibly right now, let's see if we're picking up the audio. It is. Introduce yourself and ask the question. Sit in the chair.
Scott, this is Bart Ballard. I'm wondering, would it be useful to use two detectors and a red and a violet filter for comparison?
Yeah, I probably want to put the camera on him when he was asking this question, but.
No, the whole frame will fix it over.
Right. Aha. There we are. Looks like somebody said can't hear. I need a mic. Scotty, are you hearing me okay? Moderator, please turn Scotty's mic back on. We didn't turn it off, so sitting here and I think maybe we've got a problem. See if I can figure out why this is.
That fixed it. Assuming y'all can hear me now. Yeah, it was grayed out. I wanted to answer, but couldn't. The answer is yes. This season, now that we are well aware that the scattering is occurring in shorter wavelengths, we are going to request, and this is a conversation outside of this conference. Feel free to join us on our discussion group, but we are going to do multicolor observations in all filters simultaneously with multiple observers so that we can publish our paper in Icarus demonstrating where the scattering effect is taking, being able to actually determine particle sizes by the scattering relative to the difference in the blue scatter versus the violet scatter. And the answer is yes. I'm actually assembling a rig right now that will image Jupiter in 5 different wavelengths at exactly the same time with 5 different colors, 5 different recording systems, and that will pinpoint all of that information. But if you cannot do filter work, then just use it unfiltered. And anyway, feel free to, we can talk about this later, because I know y'all probably want to get on. Well, a lot I could talk about, there's just not enough time. Thank you. I'll put out a teaser there, by the way. We also have a major paper coming out now. We've discovered the ability to detect water geysers on Europa. So I'll leave that as a cliffhanging teaser.